And so now for maybe a breath of fresh air a little bit, as far as a new use case or implementation idea around using SDN for service provider deployments, Jen is going to describe work that she's been doing on a software-defined exchange.
Thank you.
Yeah.
So SDN has been really radically changing the way we design and manage networks, and in backbones, data centers, and even enterprises. But most of the work that's been taking place to date has really been focusing inside an individual one of these networks. Network virtualization, network function virtualization, traffic engineering, better monitoring, and so on. What I want to talk about today is taking things to the next level, to really fundamentally change the way we deliver traffic over the internet, the way domains interact with one another to do end-to-end delivery of traffic. And I want to do this in a particularly strategic way, because we're certainly not going to do a forklift upgrade to the entire internet to running SDN. And it's not even clear if that's really necessary or even will ever happen. Instead, really, our goal is to look at what we can do strategically by putting SDN functionality at the juncture points between domains, at private peering points, or more specifically in this talk, at the internet exchange points where dozens or even hundreds of networks meet to be able to exchange traffic and routing information. So just a quick primer on the internet. The internet is really 50,000 or so separately administered networks that are part of a competitive cooperation with one another to get traffic from one end of the internet to the other. And the protocol that navigates this is the Border Gateway Protocol, or BGP. And so BGP allows a network to advertise a big chunk of addresses, an address block, a prefix, from one end of the internet to the other, where each domain receives an advertisement from its neighbors, picks amongst the routes available to it the best one from its point of view, and disseminates that to its own neighbors. And so in this sort of hop-by-hop fashion, the information percolates across the internet to the point that a web server in Autonomous System 6 might have a 6-hop path back to reach a client that's in some address block over in Autonomous System 1. So BGP's been around for about a quarter century, and frankly, it's showing signs of age. And there are 4 real key ways where it's not standing up to the challenge that service providers have today to deliver content to their users. The first is that as I showed in the slide before, the routing is done only on destination address blocks. That's a very, very coarse grain of doing internet traffic delivery. It doesn't allow us to think about applications or senders that might have different performance requirements or security requirements than other applications or senders in the same address block. You can only indirectly influence your immediate neighbors. You decide what to announce to your neighbor, but you can't influence what somebody many hops away from you decides to do. You don't have direct control. They're fairly baroque mechanisms for taking a bag of routes you learn from your various neighbors and indirectly deciding which one might be best and then populating the forwarding tables, but you can't just directly say what you want the network to actually do. And finally, you really can only control packet forwarding. You can say this traffic should go this way or that way, but you can't decide traffic should be dropped or modified in some way or given a different quality of service. So you might say, who cares? The internet really is only there to do end-to-end delivery in this coarse-grained way, so why do we care? But the bottom line is, as we talk to service providers, there are a lot of things they wish they could do, and the way we do inter-domain traffic delivery today is in the way. So really simple example, application-specific peering. I connect to a peer at a relatively low bandwidth, but I can give really, really low latency. I don't want to have video traffic go over that path because there's just not enough bandwidth to sustain it. So I might want to send my video traffic to one peer and my non-video traffic to another, even if they're in the same address block. Really simple idea, but difficult to do with BGP. I might want to block denial of service attacks. I have unwanted traffic that's coming into one of my customers' networks. I want to reach really far upstream and drop it early before it consumes any bandwidth on my customer's network or even on my own network. Again, something BGP doesn't let you do. Server load balancing. Instead of relying on something like DNS to decide which client goes to which copy of a website in 2 different data centers around the world, I might want the network to be able to decide which traffic goes to which copy of a web server. Steering traffic through network functions. I may want deep in the middle of the network to do scrubbing of suspicious traffic, transcoding of high bandwidth video traffic, caching of popular content, encryption for customers that need better security, and so on. And finally, we also hear about service providers that connect in multiple locations that would like to have selective control over which traffic enters their network at which location, not purely based on destination prefix, but based on sender or on application. So for all of these examples and more, SDN offers exactly the functionality we need. And there are really 4 key things that SDN brings to the table. The first is the ability to match packets on multiple header fields. The destination prefix, sure, but it's not the only field that matters in deciding how we want to deliver traffic. So we'd like to be able to match on all the fields in the packet header in deciding how to direct traffic. We'd like to be able to control entire networks with a single program, not a single router or our relationship with a single neighbor. We'd like to have direct control to actually tell the switch exactly which traffic we want to go where, rather than having to configure fairly Baroque arcana in BGP to make those same decisions. And finally, we want to do more than packet forwarding. We want to drop unwanted traffic. We want to modify a VIP to a DIP to get traffic to go to a particular website. All of these things are very natural to do with the simple match action abstraction that interfaces like OpenFlow offer. So the idea that we have then is to bring SDN together with the way carriers exchange traffic with one another and with content providers. And so the strategic idea here is to do this exactly at those juncture points between domains. And the reason we want to do this, particularly at exchange points, is these are places where dozens or even hundreds of different service providers and content providers meet to exchange traffic. So if we can deploy an SDN-based solution at even one of these big locations, we can already make a difference in the services these networks are capable to offer, and to make benefits for many, many different parties, not just one. And most importantly, we can do so without those carriers having to deploy new equipment. They're just going to connect to the exchange, and it's the exchange point that is doing the SDN deployment. It's not the carrier doing a forklift upgrade of all of its legacy routers to support SDN. Or it's a carrier doing this at a private peering point in between their legacy router and the legacy routers of the peers they connect with. So much, much better proposition for doing SDN deployment. So why do we want to do this particularly at exchange points? Well, exchange points are really a hotbed of innovation, particularly in the last several years, primarily because of the increasing amount of video traffic on the internet. And so they're right at the center of disputes over who should be paying for the delivery of video traffic and who should be carrying what traffic to whom and with what level of performance. And so these IXPs have been growing in number and growing in importance. There are around 350 to 400 of them around the world today. Many of them are bigger and carry more traffic than tier 1 providers. And there are 100 new ones just in the last few years. Why? Because of video traffic and because of the effort to get the next billion people on the internet, where we don't want traffic between two different carriers within a single continent like South America or Africa to have to go through another continent to get delivered. So the need to keep local traffic local is driving the deployment of these exchange points even in the developing world too. So realizing these things, a group of us got together to create an open source platform for doing SDN-based internet exchange points. And we have a paper at SIGCOM, and I'm just going to give you a high-level overview of what we've done. And I want to stress we're not the only people thinking about this idea. There's an SDN-based exchange points in Australia and New Zealand. There are people in Europe. There are people looking at connecting the research and education networks in the US to Latin America and to Europe and so on. So there's a tremendous amount of momentum in this space to be able to think about new ways to use SDN to interconnect the different parts of the internet. But I'm going to tell you our take on the problem next. So what is an exchange point? Well, an exchange point at a high level is one or more switches that connect a bunch of autonomous systems together. So each AS has one or more border routers that can just be legacy BGP-speaking routers that connect to an Ethernet switch at the exchange. This Ethernet switch is just providing basic connectivity with no particular data plane functionality, just MAC address-based forwarding between the border routers of these different domains. And there's also a route server that is allowing, instead of all pairs of these networks to speak BGP with one another, they all speak to the route server and they all tell the route server their policies, so the route server can make decisions on their behalf. It's just a more scalable way for all of these networks to exchange routing information with one another. So this kind of looks like SDN already, right? We've got a control plane separate from the data plane. But the key point here is the control plane is only doing BGP, and the data plane is only doing basic connectivity. So at some level, all we're doing is souping this up a bit. We're going to deploy an SDN-capable switch that can do match action processing on a lot of different header fields. And we're going to soup up the route server to include some SDN control functionality. That's it. Notice there's no change in what's going on in any of the autonomous systems that connect to the exchange. All the action is taking place on the SDX controller that's operated by the exchange point provider. Okay, so I want to give you two example applications to go back to the ones I mentioned earlier. One is DDoS mitigation. So we have a victim that has a denial of service attack being launched against him, maybe a customer of AS1, maybe someone that's not even connected to the exchange. They've recognized that a certain set of traffic coming from a certain set of flows is unwanted. They can reach out to the exchange point and essentially say, I want this traffic blocked. This is just the installation of some match action rules that match on the unwanted header fields and have an action of drop. And that's it. And you can do this potentially at multiple exchange points, not just one, because the attacker may be coming from a lot of different vantage points on the internet. So this is not a very deep idea, and in fact, that's part of the point. This is a very simple idea that's actually very difficult to deploy today. but it's actually trivial to deploy with an SDN-enabled exchange. So why is this better than what people do today? Well, first of all, you can have remote influence. You can go from a victim several hops upstream and say, I don't want this traffic. You don't even have to be a physical member of the exchange. You just need to have some sort of business relationship. The second thing is you can be much more specific than blocking on an entire destination IP address block, which would have a ton of collateral damage of traffic you actually do want to receive that has nothing to do with the attacker. So you can drop on all the different header fields that an SDN switch is capable of matching on, rather than just on something like destination prefix. And finally, you can do this in a coordinated fashion. If you've got multiple places around the internet that are able to do this for you, you can go to all of them and block the unwanted traffic around an entire perimeter, sort of a circle of defense, if you will, around your network. So that's just one example. And just to take a slightly more sophisticated example, let's look at inbound traffic engineering. It's a little bit more nerdy of an example, a little less customer-facing, but still important. So a carrier might connect to the exchange at multiple locations, either two routers in the same city, or in fact, some of these exchange points themselves are physically distributed over multiple cities. And so there's a block of addresses that are reachable now via two different links. The carrier wants to decide which traffic goes through which link. BGP is not going to let them do that. It's going to do it based only on the destination address block. Now, why does the carrier care? Well, maybe behind one of these connections is a block of customers, and behind another is a separate set of customers. Maybe they'd like to divide the traffic based on which customer is sitting behind each of those routers. Or maybe one of those routers is connected to a video transcoder. And so it'd be really natural to steer the traffic through the link that goes directly to the middle box that you actually want that traffic to be processed by next. Or maybe the carrier just knows the distribution of traffic demands cut along a different dimension than destination prefix. Whatever the reason, it would like to have the control to be able to do this on something other than destination prefix. For example, let's suppose we want web traffic to go out one link and non-web traffic to go out the other. With BGP, you're out of luck. You just can't do it. With an exchange point that has SDN, this is, again, just a simple match action rule, matching on the header field of interest and forwarding out the link of interest. So those are just two examples. I'm just going to briefly summarize some of the work we've been doing on building platforms that can support these applications. And this is difficult because we need to offer the right kind of programming abstraction so that each of the carriers that's a stakeholder in how the traffic should be handled have an opportunity to weigh in and not overstep and influence too much what the other carriers can do. And I'll talk briefly about that. There are two other issues. One is, if we're going to do this on an exchange point, we have to play nice with the rest of the internet. We can't break BGP in doing this. We can't create forwarding loops, protocol oscillations. And there are a number of fairly subtle technical issues there that are described in our paper. And finally, this has to scale. These exchange points could easily have hundreds of participants with 500,000 address blocks, and we're going to make that even worse by now matching and acting on other header fields besides the address block. Here we've got a number of really clever tricks to take advantage of the fact that there's a BGP router all around the perimeter of these exchange points that are already maintaining state on a per prefix basis because they have to speak BGP within the carrier's own network. So we leverage that to essentially create a multi-stage table where we put some extra work, unbeknownst to the carrier, on their router to tag the packets on our behalf, to be able to, without changing BGP, allow us to get by without having to put millions and millions and millions of rules in commodity OpenFlow switches. So I'm just going to end by talking a tiny bit about the abstraction that we provide. And the high-level idea is we want to give each of the parties at the exchange the illusion that they have their own switch. Simple idea, virtualization. But here, instead of having one virtual switch mapped to many physical switches, we have one physical switch or a set that have multiple virtual switches associated with them. So the idea is that each of the networks here has its own virtual switch, almost an extension of the carrier's own footprint, that they have the luxury of installing rules on without having to deploy any equipment of their own. And so that's also providing isolation because autonomous system A can only say what the virtual switch connected to its own port can do, how traffic coming from A should be handled, or traffic about to be sent to A by someone else can be handled. And so in this example that I had, sorry, let me go back. We want to have traffic go, let's say that ASA wants web traffic to be forwarded to C, C wants web traffic to be forwarded out a particular link. We'd like the illusion that packets will hop from one to the next. But in practice, there might be only one switch here. So we don't really want each of these virtual switches to be implemented separately. Instead, we need to synthesize one set of rules that will implement the collective functionality, which here is just matching on both fields where the traffic's coming from and whether it's web traffic or not, and forwarding it out a particular port. Let's suppose autonomous system A wanted to drop all web traffic. Well, it got to go first, so if it chose to drop the traffic, it doesn't matter what C would have chosen to do with it, because C wasn't the recipient of that traffic. And so we would instead install a rule saying traffic coming in on port A with destination port 80 would just be dropped. And so we can imagine synthesizing these policies and do an OpenFlow 1.0 switch, or better yet, into a multi-stage table, or in better yet still, into P4-enabled switches that have very flexible match action processing on multiple tables to be able to implement this efficiently. So to conclude, basically the ability to provide this abstraction and to be able to solve the scalability and interaction with BGP problems that I mentioned earlier are what we need to be able to build an exchange. And so we have open source software packages available at sdx.cs.princeton.edu. We have a VM you can download and play around with. And my colleague Nick Feemster, who has a very popular SDN course on Coursera that's operating now, has an assignment using the SDX. So if you want to build an SDX application, sign up for his Coursera course. And we also have done some experiments in the wild using the transit portal with a /21 address block that we get to play with. We're looking at a deployment on the Princeton campus network. We're working with some collaborators in the DoD and intelligence community to deploy this with an eye towards particularly DDoS mitigation application I mentioned earlier, and also working with partners that are connecting to exchanges in Latin America with the goal of being able to support research and education traffic between the US and particularly Brazil. So I'll stop there, given I'm already over time, and I imagine we're only going to have a moment for questions.